Okay, finally we can start. Yeah. So from today, I'm talking about rudimentary knowledge for LSI Design. It's maybe 90 minutes times 10 lectures. First, when I was a student, my professor told me that never trust simulation results. Never trust simulation results other than the ones you make by yourself. So at that time, we made our simulator by our own. But recently, it is almost impossible because we have plenty of simulation. We have to use plenty of simulations. So maybe I'm not saying this, but I'm saying to you that at least you have to understand the background, how simulator calculates the results. And every design data should be reflected on the CAD tools as the design data. And recently, the ability to design circuit is almost equal to the ability to use CAD tools. So maybe the CAD tools are your friend. So you have to know about CAD tools deeply and correctly. And this is our main target of my lecture. And in order to design the circuit with confidence, first we have to understand the physics of transistor circuits. This is the first thing. And then we have to understand the principles of CAD analysis, means how CAD tools calculate. And then we have to understand the relations of input item. We have to input many things on CAD tools. And we have to understand what CAD item means and its relation with physical things. And then we have a simulation result, and we have to judge whether the output from CAD tools are correct or not. We should not blindly believe the CAD tool result. We have to doubt about the result first, and then judge if it is correct or not. So in order to do this, we have to have a kind of rudimentary knowledge in each phase. And each phase means, and this lecture does not contain the operation principles of transistors. Maybe all of you, except you, knows about transistors. I'm assuming all of you knows about transistors. The transistor about stretching depletion regions and how to form a channel and how to go current from source and drain. It does not contain my lecture. And circuit itself, such as common source, what is common source and what is common source followers, and how what is AE and DA and DLL. I'm not saying about this. And also, I'm not talking about how to use CAD tools. Click this button and put a menu and select this and input blah blah blah. I don't say about this. So what I'm talking about is first, we have step by step for the design a circuit, and maybe you are a circuit designer and you design a circuit. First, you have schematic entry by cadence. And then you run spice simulations, and then you draw layout. And after layout, you will run LV and DLC as verifications. And after that, we run RC extraction to estimate the effect of wire R and C. And then we have to know about I/O buffers, what kind of I/O buffer we have to use. And usually this is the end of design, but we have to think about noise. There are many kinds of noise, and we have to design a noise immunity circuit. So we have to know about noise. And also recently, we are using about 90 nanometers 45 nanometers, 28 nanometers, we have plenty of problems. So I'm talking about the problems on advanced CMOS technologies. And this is the, from here, this is the design side. And after design your circuit, you fabricate a chip, maybe you don't fabricate, you ask someone to fabricate. But once you have real LSI chips, you have to measure it. And there are many techniques about measurement. So first I'm talking about what kind of devices we have and what is it for. And also there are many measurement techniques. And at the end, I'm summarizing about the overall flow of those steps. So I want to know about you. How many of you have experience in schematic entry in cadence? Maybe all of you. How about spice simulation? Okay. Layout and LVS DLC.
A little bit.
Maybe half. And idle buffers. No one. And think about noise, like power supply noise, substrate noise, many kind of noise. Okay. And how about NBTI, random telegraph noise, and such kind of problems. Okay. And how many of you have experience of the major real frequency? Okay. So maybe each step I will talk about the 20 minutes, 90 minutes per each stage. So we have 3 hours per day times 5 days. So today I'm talking about schematic entry and spice simulation. Okay. So the lesson 1 is schematic entry. And what we will learn in this lesson is about like this.
Okay.
Maybe the circuit is only, the circuit in my lecture is very simple, inverter or NAND gate, or inverter chain. That's all. But before designing a circuit, in my laboratory, I'm asking students to install operating system first. What kind of operating system do you use? How about it?
I use Windows main OS. However, I use Linux on the virtual machine.
Okay. And for circuit designs, maybe you will use Linux. Maybe Windows does not work for circuit design. So first we install operating system, and most of them does not know about Linux. They are used to Mac or Windows. So the first thing you have to do is learn about the Linux command, copy, ls, pwd, and so on. And you set .cclc. And you are used to VI or Mule text editors, and install CAD tools, and it takes about a week. And finally, after 1 week struggle with these things, you finally input virtual and return. It takes 1 week. And then, finally, you put transistor symbol on schematic digital like this. This is PMOS and this is NMOS. And the first question you may think is, what is this? In your textbooks, the transistor symbol has 3 terminals, gate, source, and drain. But on the schematics, you have 4 terminals, gate, source, drain, and body. What is body terminal means? What is body terminal?
body.
B.
B.
Yeah.
Yeah.
Do you know what B means?
B body.
Body. What is that?
Yeah, the terminal and the bottom of the center.
Okay. And usually the textbook has three terminals, and maybe you may ask to your friend what is this and what to do with this. And maybe you were told that the body terminals of PMOS should be VDD and the body terminal of NMOS should be ground. No reason, sometimes. But we have to understand what is mean. And this is a cross-section of transistors. Usually we have P substrate and source and drain on, this is NMOS. NMOS is on P well, and PMOS is on N well. And the body terminal means so usually the P substrate is grounded. So the NMOS body terminal is usually grounded. And also PMOS body is tied to VDD usually. So this symbol, you have to imagine immediately from this symbol to this cross-section. So the first terminal is body and N well at PMOS, it means N well and P well voltage. And it is biased through this well is biased through this body contact. Usually we cannot, this substrate is usually always grounded or floating. And so we have to give voltage to this from the body contact like here and like here. And in this structure, the P substrate is all common, and P well and P substrate is only realistic. So all NMOS body should be terminated to ground. And on the other hand, the PMOS body is not always VDD. You can use any body voltage from here. For example, we often want to use half VDD for analog circuit, like bias voltage or something like that. But anyway, in the analog circuit, we often want to make half VDD. And in order to make half VDD, we often use this kind of circuit. In this circuit, if you connect the body terminals like this, the characteristics of this PMOS and this PMOS becomes different. Because the source to body voltage is the same here, but it is different from here. That means the PMOS characteristics of this and this are different, and the output voltage is not become half VDD. So in order to make half VDD, both PMOS should have exactly the same characteristics. So in order to realize that, we connect these body terminals here. So that the source and body terminals are shown here, and the source and body are shown here. So, and in this kind of circuit, we can make this P well, and we will make this P well voltage is controlled independently. And this way, in this way, we use PMOS. We cannot use NMOS because NMOS body is always tied to ground. So NMOS is kind of like this. So we cannot make a half VDD by using NMOS connection like this. But sometimes we have some special process technology called deep N well. And deep N well means we put deep N well other than regular N well. So that this P well could be independent from substrates. So by using this deep manual, we can control this body bias as well. But we need special process, so we need additional layout, and it's a little bit troublesome, and it makes some kind of mistake. So as far as it is possible, we want to avoid using deep manual. We just want to use PL anyway. And after knowing about the cross-section of transistors and the meaning of body terminals, and this is the symbol of NMOS. And when we see the property of this NMOS, we have plenty of things to input. And we are very confused when first see these properties. And we are getting confused and at a loss what to do. But there are too many, and some of them are not used at all. But some of them are very important. So the important ones are the first model name and multiplier, width, length, and drain diffusion area, AD, source diffusion area, AS, drain diffusion length, PE, and PS. And these 1, 2, 3, 4, 5, 6, 7, 8 items are different. And other than this, you can ignore. So first we will see one by one. The first thing is gate length. Usually we use minimum L. It is decided by a process technology. When we use 0.18 micron, L is usually 0.18. When we use 45 nanometer, L is usually 45 nanometer. But sometimes we want to use a round number. So for example, for 0.18 micron technologies, once we put 0.18 on the layout, we have to draw 0.18 transistors on the layout. But on the layout, we have to, we want to use a grid. And if we use 0.1 micron grid, 0.1 micron grid, we cannot draw the polygon on 0.18 microns. So in this case, we sometimes use L is 0.2. And so L drawing is 0.2, and we have another parameter called LD as 0.02. So that in the SPICE simulator, we specify L equals 0.2 on schematics, and we give another parameter LD, so that in the SPICE simulation, it simulates as 0.8. So once you have SPICE simulator, you have to check if there is LD parameter is there, what is LD parameters, and what kind of layout we have to use, and what kind of L we have to use. We have to check it before starting your design. And some analog circuit does not use a minimum L. For example, when we consider about variability of transistors, maybe large L means less variability, so we want to use larger L. Or some analog circuits that has more flat ID curves, we want to use larger L to have large gain. And the next one is gate width. And usually we have to consider about, when we consider the delay time of inverters, the reason to have delay is capacitance of wire and capacitance of input, capacitance of the next stage. So we want smaller C or larger transistors to have high-speed operations. And once we have large W, we have large current, but at the same time we have large input capacitance. So large W does not mean it's operating cost, because you will have a large input capacitance. However, once we assume there is a wire here and there is a wire capacitance, and the wire capacitance is the same, independent of the transistor width, the wider W makes the wire capacitance relatively smaller. So that means large W enhances the speed, but considering the power line area, we want smaller W. So if you want to have a high-speed circuit, you use large W. And if you want to make the circuit less power and low power design, you use small W. And usually the NMOS W is usually 5 to 10 times larger than usually.
In some process.
I'm sorry?
You mean the wire of the NMOS usually have 5 or 10 times of L language of
Yeah.
in some process or in any process.
This is, for myself, this is universal. So 0.18 microns, the WN is about 1 micron. And 90 nanometer process, WN is about 500 nanometers. So when you see the layout, the ratio of L and W is the same. It is independent of the process technology. And WP, usually the mobility of PMOS is less than the mobility of NMOS, so we use larger PMOS compared with NMOS. And WP is usually 2 or 2.5 times larger than the W of NMOS. And this value is very important. So we have to simulate again and again by sweeping this PMOS and we want the same characteristics as PMOS and NMOS. I mean, same characteristics and meaning that the hold time and rise time should be the same in order to have balanced circuit for NMOS and PMOS. And next one, and we have the parameter M, multipliers. And sometimes we want to use large W like this. And in this case, here, this is a thin and long wires. So we have resistance here. And sometimes this resistance degrades the performance of these transistors. So we don't want to use this kind of large layout, but we want to divide this into 2 PCs and connect power like this. So that the gate's resistance gets smaller and you will have a better performance. And in this case, when you input the schematic entry, the long W1 transistors is the same as the half long 2 parallel transistors. But once you input like this on schematic entry, the SPICE simulator thinks 2 different transistors. And it takes time to simulate two different transistors. But actually, this is the completely parallel, so the spice filter does not have to simulate two times. But so in this case, we use half length and m equal 2. So that spice filter has only one symbol and it simulates only one time, so that we will have faster simulation speed. And also it is easy for design and easy to change this number. So we strongly recommend you to use m equal 2 like this. Don't use this schematic entry, but you use one symbol with m. And other than that, transistors are kind of current source, but transistors work as a capacitor. And there are many capacitors on transistors. Like this is the cross section, this is the gate and source, and this is the SDR. And there are many junction capacitance like here and here and here and here. And this is the top view. And we have this is the PN junction, and PN junction have always come with capacitance. So CJA means the junction capacitance per unit area. So here there are many capacitance, and the total capacitance of this drain area is the junction capacitance per area times area of drain. Meaning the area, this is the area of source. So the capacitance per unit area times area means the capacitance of total this area. And then we have also the side capacitance like here and side capacitance between the drain to gate. So the CJP means the capacitance in this area per unit length. So CJP times the peripheral, the length of this area, meaning the capacitance of this side area. And usually the capacitance per unit length on this side and this side are different. So this side and this side is different for the concerning about the capacitance per unit area. So CJP means the capacitance per unit area on this side, and CJG means the capacitance per unit length on this side. So the total capacitance of drain is becoming like this. And so we have AP, AS, PD, and PS, meaning area of drain, area of source, peripheral length of drain, and peripheral length of source. And with these parameters and these capacitance values, spice simulator automatically calculates the total capacitance and calculates the delay. So in each transistor you have to input these values, but it is sometimes very troublesome. So in some models we can use HDIF parameters, and HDIF means usually the distance between the edge of gate to the center of the contact is decided by process technologies. And so the process, once you have a process technologies, this value is decided. So once you decide this, you can automatically calculate the area of source and area of drain, and from once you know the W, we can calculate the peripheral length. So if your if your spice parameter has HDIF, you don't have to care about ADS, PSPP. And if your spice group that does not have HDIF, you have to input these parameters. And if there is no HDIF, and if you don't input ADS, PDPS, Spice Simulator thinks all of these are zeros. So you will have very fast delay and fast operations, but only on simulation. So only on simulations it operates about 1 gigahertz, but you fabricate it and actually the transistors have these capacitance and you will have only 500 megahertz and your design fails. So before starting your design, you have to check if HDIF parameter is on the parameter. And otherwise you have to input this.
Teacher, all of the parameter will belong to the frequency or not?
Okay. Usually, all these parameters are independent of frequency.
Yes.
So once you have C, the high frequency can go. The impedance of C is considered as J omega C over 1.
Yes.
So that kind of calculations are done by simulator automatically. So the parameter itself are frequency. So, and then we have to consider about models, model name. And there are many kind of models. And first, what does model means? And model is physics. And model is a mathematical expression of physical phenomena. And ultimately, all the model is the approximation of Maxwell equations. So solving Maxwell equation is always correct, but it takes very, very, very long time, and it's impossible to simulate whole the circuit by using Maxwell equations. So we want to simplify the Maxwell equations into some kind of very simple equations. And for example, maybe this kind of IDBD curve are the first thing you learn in textbook. And after that, maybe this is not flat, so the model includes this, so a little bit complicated compared with this. And or you want to use more simplified model like straight line like this and like this. And any model are okay as long as you can simulate correctly and your final performance matches with your specifications. So SPICE simulators have a variety of models. Level 1, level 2, level 3, and eSIM 1, 2, 3, 4, and level 58 and something, level 64. Many kind of models. And so in our circuit design, we have to specify which kind of model we use and which kind of models are assigned to each transistor. And usually the transistors are converted into current source and capacitors and resistors like this. So in the SPICE simulator, the transistor is replaced with voltage-controlled current source, capacitance and resistance. And first so this current source and capacitance. So we are first taking a look at this current source. And the transistor current model are very wide variety of models. And level 1 is the most simplified, and this is the first thing you learn in the textbooks. And it has this kind of equations and this kind of IDBD characteristics. Maybe once you learn about this.
There is a mistake on your slide.
I'm sorry?
There is a mistake on your slide.
Where?
The second.
Here?
Yes. If VD equal VC minus VC threshold, the ID equal 0.
V threshold minus V threshold, not VD.
Maybe 1 over 2. Yeah, 1 over 2. And this is level 1. And maybe 30 years ago, we used level 1. But recently, we use VSIM 3 and VSIM 4 models. And it is very, 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 very complicated. And actually, I don't understand the detail. I just use it. I don't understand all of the models. But we I'll talk about it later. And then we have capacitance. And usually the capacitor model is simple. And it has usually PN junctions. So the PN junction model is always the same, independent of process technology. Usually we have a PN junction like this, and there's a depletion region. And the edge of depletion regions, we have this is a kind of plate here and here. And once we increase the reverse bias, the depletion region stretches, and the equivalent capacitance becomes smaller. So usually the capacitance depends on the reverse bias. The small reverse bias means small depletion region, and we have large capacitance, and increased reverse bias between stretch the depletion region, and we will have a smaller capacitance, and so the capacitance curve is becoming like this. And this is equations like this: Cj0 and this is built-in voltage and reverse bias voltage, and the ratio of this curve is expressed like n. And the total charge necessary to switch from 0 to high is the integral of this depending on reverse bias. So when we want to estimate how many charge is injected or coming from on this PN junction at one switch, we have to calculate this. And okay, the junction capacitance depends on reverse bias voltage, and this M is decided by how this P region and N region are divided. And when the P and N junction is step change, like completely, this is completely P and this is completely N, the M becomes 1 over 2. And the P density and N density changes as linear, it becomes 1/3. So most of actual cases between 1/3 to 1 second. And once we see the SPICE simulator files, there is this kind of parameters, so we want to check this first. So again, we are going back to the source and drain PN junction capacitance. We have the area of junction capacitance and the junction capacitance of peripheral unit area and peripheral gate like here. So each capacitor has its own parameters like this. So all of these are kind of PN junction capacitance, so it has all the same model but different parameter value. And the next one is transistor gate capacitance. Gate capacitance has also many variety of capacitance model. When, for example, let's say talk about the NMOS. And when gate poly is bias minus, this is the accumulation layer is here, and we have capacitance between gate and channel. And in the off state, we have depletion region like this. So the capacitance from gate is the sidewall and overlap region and drainage, and also the against the depletion region like this. And on the linear region, we have capacitance of here and here and gates to channel like this. And also in the saturation regions, we have many gates to channel capacitance on the source side, but less capacitance on the drain side. So, and gate capacitance depends on the gate voltage. And also we have to consider about the channel charge here. And channel charge here, so, and this channel charge sometimes come from source or sometimes come from drain. It does not come from bodies. It takes very long time to come up this charge from body area. Because this is PMOS P area, and P area can have electrons if we apply a very deeply plus bias, but it takes long time, and usually this carrier coming from source or drain side. And the ratio of this charge is decided by XQC parameters. And usually this charge is half by half from source or drain, but sometimes a little bit larger from source side. So usually XQC is about 0.4, so that the 60% coming from source and 40% coming from drain. And each bias parameter has this kind of parameter, and you want to check this parameter before starting your design. And it sometimes matters when you design kind of sample and hold circuit or switch capacitor circuit. And such kind of the capacity store the charge like sample and hold and switch capacitors. This parameter sometimes matters. And again, this is a summary of the gauge capacitance. And the gauge capacitance value depends on the gauge voltage. When accumulation, we have COX, and when off state, we have depletion region like this, and in the saturation region, we have channel charge and something like this. So what I want to say here is that the gauge capacitance depends on the gauge voltage. So when we use inverted chain like this, and in the textbooks, we usually assume that this input impedance is expressed like one capacitance here. And we calculate the delay using this load capacitance. However, in actual circuits, the load capacitance is not always terminated to ground. So the PMOS, some PMOS are terminated to VDD, and some terminals of NMOS is terminated to ground, and there are many this kind of connections. And also these capacitance values depend on capacitors, depend on the gate voltage. And gate voltage meaning first meaning of this, and the second dependence means the PN junction bias dependency. So all of these bias voltage dependency should be calculated when you use this kind of delay. And so this simplification is very simplified. And actually we have this kind of more complicated capacitance network, and these capacitors depend on the gate voltage. And the resistance, we have resistance from on this source area and drain area, and also we have resistance in the body area like here. And also gate area here, so this resistance depends on HDRF, and this resistance depends on W. And some models consider this resistance, and some models ignore this resistance. And in SPICE simulator, the resistance is modeled like this. But on default, resistance is zero on default. Once you input all of these parameters, SPICE can calculate. Okay, so the next one is SPICE parameters. So once you start your design, you get SPICE parameter files, and look for the SPICE parameter files. And in the SPICE parameter files, the content is becoming like this. And as a circuit designer, you have to understand what is described in these parameter files. The first, it says dot model something NMOS. And this is the model name that we have to put on transistor symbols. And on transistor symbols properties, we say there is a model name. And we have to put this name on that item. And the first thing it shows is level equals, for example, 53, and version equals 32, and something like this. And this means we are using transistor model DSIM3 version 3.2. And these are, I call these parameters are called model parameter, and these are parameter values. And in the schematics, we specify this model name. And usually, once we have all these parameters, transistor models are automatically included in SPICE simulators. So we don't have to care about equations. We don't have to care about what kind of equations we use. But we have to care about what kind of model do we use. And also, we are a little bit confused about there is many kind of, for example, NLP.1, NLP.2, .3, .4, and blah, blah, blah. There are many kind of things, and we are very confused. And it means after dot something, it should have LB, LMAX, and WB and WMAX. that means when LMW are in this area, we use these parameter values. And when LMW are in this area, we use this kind of values. So in other words, we use different parameter sets based on LMW size. But on the schematics, we don't have to put NLP.1 or NLP.2. We just say NLP is okay. And SPICE Simulator automatically use this and this based on LP and WP. And sometimes we have NLP and NHP. That means NMOS low power or NMOS high performance, and something like this. We have different parameter models. And of course, in this case, we have to use different layout for each transistors. But sometimes we have many kind of transistor available. And in this case, in the low power blocks, we use this model, and for high performance blocks, we use this model, and we can combine it on the same chip. And also, we have a process corner library. And maybe I'll talk about more detail in the later sections. But saying that sometimes the process sometimes it becomes the typical values, and sometimes the fabricated result is high performance, and sometimes it's low speed. So that kind of variability is included in the library. And in this case, library and typical means the gate oxide thickness is about 10 nanometer. But when sometimes the gate oxide thickness becomes thicker, or sometimes thinner. And so this kind of process variability is included in the library parameters. And library this is kind of a simulation conditions. So this library information should not be included on your schematics. On the schematics, we assume all of the transistors are fabricated by typical functions. And the slow function and fast function should be specified by another stimulus of the simulator. And this value sometimes use sigma, or sometimes 3 sigma is used. So you have to, maybe these sigma or 3 sigma are in the document. So you have to, once you want to know about the variability of the process variations, you have to consult with the manuals first. And this means the sigma or 3 sigma. And this is, once you start your real fabrication in mass productions, this value becomes very important. Okay, so here for example, vSIM 3 and vSIM 4, and maybe in the future we will have vSIM 5, 6, and 7. And they are very complicated, and it's almost impossible to understand all of this. But some point we have to understand. For example, there is a gate, and I said that there is a gate resistance here. And some models include gate resistance, and some model does not have gate resistance. For example, vSIM 3 does not have gate resistance, and vSIM 4 has gate resistance. And also there is a lead from gate to channels. And this lead is considered in BSIM4, but BSIM3 does not have this kind of gate. So once you start very high-speed circuit design, and you have to consider this OR gate, you have to put, if you use BSIM3 model, you have to explicitly put resistance symbol on schematic. We want to consider this resistance. And also there is a, if you are interested in low power and you have to care about the leakage current, if you use BSIM3, you have to explicitly conductance between gate to source or gate to drain on the conductance. And if you use BSIM4, this gate is automatically included, so you don't have to care about it. Or this kind of body resistance, or there is a junction P-well and N-well junction capacitance. And well to substrate capacitance, there are many kinds of capacitance here. And these are not considered on BSIM3 nor BSIM4. So if you are interested in substrate noise, for example, you have to explicitly put this resistance on schematic bias. And if you want to, for example, bias the PMOS body and dynamically control this PMOS body, these capacitors limit the breaking frequency. So you have to explicitly put capacitance values here and put resistance values on your schematic, because these are not included on the SPICE simulators. So you don't have to understand all the equations, but depending on what your circuit targeted, you have to understand this model is included or this model is not included, and you have to put explicitly R or C or something like this.
This means that the higher level of model, we will have more accurate of simulation. So, in which case we will use model? I mean that the higher level of model we will have more accurate of simulation.
Yes. So in advanced CMOS technology, there are many physical phenomena appeared when we have fine pitch transistors, and these phenomena are included in advanced models. So maybe if you use point, for example, 1 micron technologies, level 1 might be enough. But once we have 28 nanometers, there are many kind of the physics in 20 nanometers and physics in 1 micron is quite different. So the physics are different, so we want to use different models. And usually once we decide which kind of fabrication factory we use, for example, if we use TSMC provides the parameter files, and we have to use this kind of models. So actually we don't have, we cannot choose model.
It depends on the factory.
Yeah, so factory choose the model and factory make the parameter files, and we are just a user. But we have to understand what physical phenomena are included on that model. So when we design a circuit on cadence, for example, when we design like inverter chain like this, you shouldn't design like this. First you design inverter and simulate it, and symbol you put hierarchical design, and we strongly recommend you to use hierarchical design. And in Cadence, we can parameterize a cell. For example, we design inverters like this, and inverter size can be parameterized, like LP, LP, and LN, LP, and symbol has parameters like this. And put this symbol here, and we put parameters here and here like this. But I recommend you to not to use this. If you want to use different inverters, you have to make different inverter symbol, like inverter 1 and inverter 2. Because this is very, very, very confusing if you start layout. So use this. And also, sometimes we can use global connections. Like in Cadence, for example, VDD exclamation mark means global VDD. But I recommend you to not to use global. Because once we use small circuit, maybe global connection is useful. But in the end, when you design a whole chip, you want to divide the power supply. Like this area should be power supply 1 and this area should be power supply 2. If you use global, we cannot do that. So we often use, for example, a different power supply for core circuit and different power supply for I/O circuit. That is a typical examples. So okay, so here's the power to ground, put terminals. And the inverter has 4 terminals, should be 4 terminals, in, out, and VDD and ground. Should be have 4 terminals. And once we have the inverter channel like this, connects this power like this. And in most of schematic entry tools, we can have label connection. Once we put labels like this is VDD and this is it automatically connects. So you can use this kind of connections. So no global VDD and ground, but you use label connection for VDD and ground. Label is useful, but don't use labels for signals. For example, in this case, this looks very complicated. And once you have label connection, this becomes simple. So this looks simple, but after this, you have to draw layout. And when you draw layout, this schematic is very difficult to see. So you have to use this. So label connections are restricted only for VDD and ground. And signals should be connected by lines. And also, sometimes we want to cross connect like this. But don't use cross connection like this. If you connect like this, you have to shift like this. Because once we have modify or you change the scales, in this case, for example, in this case, we cannot see this is connected or this is not connected. So once we have rules, we will not use this kind of thing, and we always use this. This means no connections. So we should not use cross connection like this. Okay, this is the end of lesson 1. Any questions?
I have a question.
Okay.
Could you tell us about the disadvantage of higher model?
Higher model?
Yes.
What do you mean higher models?
For example, the BCM3 and BCM4, what's the what is the disadvantage of the BC4?
BC 3 is used maybe until 0.13, and under 90 nanometer or 45, 28, we usually use BC 4 because I'm not familiar with the detail, but the main the physical phenomena is different for above 100 nanometer and below 100 nanometers. We have many leaks, and we have many kind of resistance, and we have the ID curve is a little bit different. And the main difference for our normal circuit designers, the main difference is this. This is the gate capacitance and gate leakage. And BC4 take into consideration the gate leakage. So once we give, actually the gate leakage parameters are usually included. So once we put NMOS, it automatically leak from gate channel. But on BC3 we don't have gate leak. And for example, the gate oxide thickness is getting thinner and thinner in, for example, 28 nanometers. The gate leakage is getting apparent, and we really have to consider it for our design. So that kind of new physical phenomena are included, and the new version of model is developed. So the main difference for gate BC 3 and 4 for our circuit designer side is this gate resistance and gate leakage. And BC4 does not include this kind of RMC, so once we want to take care of the substrate noise, we have to do this.
Could you please tell us more detail about the low power set? When if we focus on the low power design, we focus on the low power design. So what kind of leakage or what kind of resistance or capacitance that we must focus on that one?
Just to explain this, before you say in advanced CMOS technology, if we use BC3, we don't have to consider about the gate resistance or the leakage from the gate to the channel. And you see, if we have to consider the high currency, we consider
focus on the resistance gate resistance.
Yeah.
Yes. So if we focus on the low power, what kind of resistance that we follow? What we will focus on that one?
For low power.
You
So
say that we have to focus on the leakage from the gate.
For low power means, for example, you when we use cellular phone, most of the time it is waiting, and only several minutes we talk on the cellular phone. That means most of the times it is on the standby mode. The circuit does not operate, but it has the gate voltage is applied. So once we ignore the leakage current, that means the standby mode does not consume any powers. But once we consider the leakage, the standby mode always have current from VDD to ground. That means the battery consumes. So once you consider this, the battery sustained only 1 hour, so for example 1 day. But once you ignore the leakage currents, the battery might have 1 week.
So we focus on the gate leakage current, and also we focus on the subject of leakage current. So that means we focus on the gauge leakage current,
Yeah.
also the structural leakage current.
Yeah.
Okay, I understand.
Any other questions? So we will have a short break. We have 5 minutes break.
Yes.